Okay, good morning, everyone. Okay, any questions before I get going? The first thing I would like to do is, before we get to new section, is a comment about the quiz. You guys struggled with the first question and the second question on the quiz. You are fine with the rest reasonably. So I will talk a little bit about the first question. So let me take an example before I talk about the answer. So let us say I take the following sequence. Sigma 1 over, let us say, n square or k square if you want. K equal 1 to infinity. Okay, let's take this series. So this is 1 plus 1 over 2 square plus 1 over 3 square plus etc. plus 1 over 100 square plus 1 over 101 square plus etc. plus you keep plus so. And let us say I told you, and this is correct, that this sum is equal to pi squared over 6, which is actually that's the value of this sum, and the proof is not trivial. It's equal pi squared over 6. What does it mean? What does this mean? What does this something like that? Somebody you pick up a math book and you find this equal pi squared over 6. What does this mean to you?
Isn't that the sum, the S?
Anybody? I know it's Monday morning, 8 o'clock. I'm aware of that.
Isn't that the sum of the series?
The sum is equal pi squared over 6. Nobody want to talk?
Isn't that equal to the sum of the series?
Okay, so I'll do the talking.
No.
So it means basically if you start adding those numbers, and we're going to add them in a minute. Actually, we're going to add them in a minute. I'm going to show you. Because if I start adding, I add 1 plus 1 over 2 square. Then I add the first 3 terms. Then I physically add the first 100 terms. Then I add the first 1,000 terms. And I keep actually adding them. The more I add, the closer I will get to pi squared over 6. So let us actually add them. I'm going to share the screen and add them with you. And let's figure this out. So I'm going to share screen. Okay. And I'm going to add them. Okay, so this is a Wolfram Alpha, which is computer algebra system, which help us to add numbers. So this is my numbers is 1 over n squared, and I'm going to add them from 1 to 100, physically adding them. So what this is going to do is add them. Okay, I get 1.6394. So I'm going to add the first 100 number, 1.6349. I'm actually adding them. That's what we're doing. Then I'm going to add the first, let us say, 1,000 term. So what this is doing is physically adding them. And this is giving me 1.64393. So honestly, I'm just adding those numbers. Like, let me add the first 1,000 term. And 1.64483. And I can keep going. I mean, actually, this is very powerful. It can add the first 10,000 term, I think. Again, first 1,000, it's going to, the first 10,000 term, it's giving me 1.64493. 92, and I keep going. Actually, this algebra system helped me to add more and more. But really, what's the point? What does this mean? If I square over 6, if I pick up my calculator and I compute this number, this is 1.64493, etc. So what's really happening is, this is exactly what we're doing. We start adding, physically adding. Those are the partial sums. So this is S100. This is S1000. That's what we call it, partial sum. This is N10,000. That's what the partial sums are really about. So we keep adding as we realize the sum is becoming closer and closer to 1.64. 64493. So what does it mean for this sum to be equal to this number? It means actually as you keep adding more and more term, the sum, the partial sum, are going to become close to that number right there. And actually it's interesting. If you guys notice, the first 100 terms, if you add them, you get 1.64393. The first 1,000 is 1.64493. So those terms from here to here, very tiny. When you add those, you have to get very, very, very tiny number. I mean, they agree on the first 2 digits. So this is up to the 100 terms. And this is up to the first 1,000 term. So between them is from the 100 term to the 1,000 term. And look how small it is. It's like 0.001 almost. That's how small it is. That's how why the series converge. It means when we start adding those numbers at the end, they are very, very tiny. Otherwise, the series is going to really diverge. Okay, so that's really a series, and that's really what's happening. So why I'm bringing this up? I'll go back to the first problem on your quiz. And my problem is sigma, suppose you're told sigma AK equal to S. That's the setting I had. What can you say, and K1 to infinity, what can you say the limit of the partial sums? Sorry, I used the number 15 here. And what can you say about the limit of the terms themselves? Okay, so basically if I take, so it's A1 plus A2 plus A3, that's what does this mean? Plus etc. The sum, this is equal to 50. So what does it mean about the partial sums? And what does this tells me about the AK? Okay, back to you. If this is 15, it means the partial sums are going to become close to what?
15.
Anybody likes to answer? The partial sums themselves are getting close to 15. That's really what it means. It means when you are adding those, it's those sums which are becoming close to 15, not the AK. It's the sum of the terms. This what we're doing is the sum of them. Do you have us? No, you can unmute yourself, Brian.
Can you hear me right now?
Nobody, you guys are muted. You cannot talk.
Can you hear us?
Yeah, no, I can't hear you yet. Can you try again? Oh, no, somehow I don't hear you at all. That's why I was sitting here. Can you guys hear me? I think you can. Can you hear me? Yeah, but okay, we hear you. No, I don't hear anybody. Allow participant to unmute yourself. No, I'm sorry. Try now. Let's see if anything changed. Anybody try to say something? Yeah, I honestly don't know what's really going on. It's never happened before. Okay, unmute yourself and try again to talk.
Can you hear me now?
That's weird.
Hey, can you hear us?
Hello.
Honestly, I don't know. I don't know why it's doing this to me. Okay, just put on chat. I'm not gonna fix it right now because I don't know how to fix it at this moment. Because I have never changed the setting of it at all. I've never touched it. So please write on chat because it's annoying this way. Okay, what about the AK? The AK will have to 0. Those terms has to go to 0. Otherwise, if those, regard, we're adding them. If those are not becoming small, forget it about the sum to converge. And the AK goes to 0. Okay, so that's what's happening in the first problem. A lot of you skipped it. A lot of you messed it up. Okay, so I'm trying to see if I can. I'm going to mute one of you. I'm going to. I don't know what's happening.
I'm unmuted. Can you hear me?
All right. Now let me look at number 2. Please keep chatting because it's annoying not to be able to hear your voices. Now, number 1, number 2, and then I move on. Okay, number 2, you did better, but I still feel there is something not clear in your mind. And my question was, if the limit as k goes to infinity of ak equal to 0, then the series must diverge. Sorry, must converge. And the answer was false. And a lot of you mentioned the divergence test, which tells us that if the limit is not 0, the series diverge, but if the limit is 0, is either way. And so false, if the limit equal to 0, it means we're adding those terms. We're adding them. AK, etc. And that's we're adding those terms. The single term become close to 0. It doesn't mean that the partial sum have to converge to something. The sum can still actually blows up to infinity. And the example we have is the sigma 1 over k. K equal 1 to infinity. Now by the divergence, by the integral test, this one diverges. However, the term are really going to 0. All right, so this was the idea. Now let me, the same way I did before, I'm going to share screen. I'm going to add the term of this sum. And I'm going to see what happened if we add this sum. The only reason we know it diverges, and that's the only reason everybody knows, because of the integral test. But let us start to add those sums and see if they are getting close to something. So I'm going to again share the screen with you and add those sums. Okay. So this is 1 over n. Okay, and I'm going to add the sum. I'm going to add the first 10,000 term and see what I get. I'm going to get 12. All right. I'm going to add more terms. I'm going to add the first, I just put my 100,000 terms. It's 14. Realize the difference between this one and 1 over n squared. Watch the difference. 1 over n squared, when I jumped, the sum barely budged. Now it's increasing, not by a lot, but it's increasing. I'm going to keep adding. And let's see what happened to the sum. Are they close? The sum is still increasing. It's at 16. We're not even, the sum is not getting close to anything. I'm adding and adding and adding. So I'm adding now the first, whatever, billion terms or something. The sum is keep jumping. So the more term I add, I don't get close to anything. In like 1 over n squared, where I really got close to something. I'm going to try one more or two more zeros. And let's see what this is going to give me. 25. You see what's happening here? So the sum is moving very slowly. That's why historically people got cheated by this sum. It's increasing very slowly, but it's increasing. It's never stopped increasing. So if I add two more zeros, I don't know if it's going to do it. It's jumping to 30. Okay, we're not getting close to any fixed number. This series is going to keep growing and growing and growing. It never had up. Even though the terms are small, intuitively, they are not very small. All right, so this is concerning the quiz. The rest is fine, depending on the student. I have the solution on Brightspace. Please look at it. All right, so before we move on to the next section, the test that we have seen so far, the integral test, so we've seen so far, the integral test. And this is what gave me everything I know about the P series. They were crucial for the P series. And they told me that those series converge when P is bigger than 1, diverges otherwise. Okay, that's diverge. And then we saw the limit comparison. And the limit comparison test was basically, the idea mainly was to compare the terms of the series to a P series. So that's why we use those as a reference point to be able to compare them with. And then we saw also comparison test. And both of them, in general, used this series and the geometric as a reference point. So we say that if my series behave like 1 over k squared, it will converge. If my series behave like 1 over square root of k, it will diverge. Now, all those tests, though, are valid when the terms of the series are positive. When the terms are positive. Okay. So if we add in positive terms to each other, then the tests are valid. For example, let's see the comparison test. Let me ask you the following. Give me an example, the best you can, of a series that said the following happened. AK less than BK. AK definitely not positive. Otherwise, what I'm asking you is impossible. I want the smaller series to diverge and the larger to converge. But be very careful, I'm dropping positive here. Okay, give me an example. I'm dropping positive, and it's absolutely crucial to drop positive here.
Can you hear me? Oh, well.
So anybody who comes with an example, please let me know. Okay, all right. Anybody else? Okay, here's an example. One of your classmates tells me, take 8k to be 1 over k, minus 1 over k, absolutely. And take bk to be 1 over k squared. This definitely holds because k is absolutely minus 1 over k is negative, and this is positive. So ak is less than bk. Now, sigma ak basically is sigma minus 1 over k. You can basically take off the minus, this diverges. Okay, because this one will go to minus infinity. However, the larger one will converge. Okay. So the positivity is absolutely crucial in the comparison test. So the term to be positive is actually making the scenario impossible to happen. So the AK in my scenario cannot really go to infinity or minus infinity, and it is forcing the situation that if this one converges, this one will converge, because those cannot blow up. So everything we've seen so far is valid when the terms are positive. So now the question is, when you start having the sign are positive and negative and everything, how can we determine whether the series is going to converge? So today we're going to see our first scenario, and we're going to see what we call the alternating series. So alternating series. So we're starting to move a little bit away from series with positive term. And today we see a very specific type of series that comes up. That's why we have to study them. Alternating series. Now, what's an alternating series? An alternating series is a series where the term alternate. An alternating series is a series where the term alternate between positive and negative. So where the term are alternately positive and negative. So what does it mean? So this is an example. It means the terms are like this. Okay. 1, for example, positive, negative. Positive, negative. Positive, negative. That's what it means, etc. So it's series where the term positive, negative, positive, negative, positive, negative. That's an alternating series. So in sigma notation, how are we going to write this series? So this is sum k equal 1 to infinity of the following. How can I write this series in sigma notation? Anybody can tell me the notation? How can I write this in sigma notation? Okay, anybody, please write it on chat. How can we write this? So 1/2, 1/3, 1/4, 1/5. So I can see stuff. Yeah, you're right, but I'm gonna, because I started at 1, yours will give me problem. Gavin, yours will give me problem at 1. So I'm gonna follow the second one. -1 to the k plus 1 over k. Absolutely correct. Now at k equal to 1, I have -1 to the power 2, which is positive, over 1. At k equal to 2, I have -1, 2 plus 1, which is going to give me -1/2, and so on and so forth. Okay, so this it's k plus 1, Brian, because -1 to the n will not do it. -1 to the n will give me a minus in here. So once you write it in sigma notation, go back and see, is it really working correctly this way? All right, so that's example of an alternating series. So terms we add, then we take away some, then we add, then we take away, then we add. So it's very different than series with positive terms where they keep growing, where the partial sum keeps growing because we're adding always positive terms. Now, however, something like this is not alternating. So this is -1/3 plus +1/4, let us say -1/5 plus 1/7, etc. This is not alternating. So alternating, it has to be past, not alternating. So alternating, they have to be positive, negative, positive, negative. They cannot be negative, negative, positive, or so on and so forth. So that's what an alternating series. So in general, an alternating series has the form. An alternating series has the form, and I will use the form in your book, which is, it's not my favorite form, but I will use it. So it has the following form: sigma -1 to the k plus 1, a to the k equal 1 to infinity. It means a1 minus a2 plus a3 minus a4, etc., where the ak has to be positive. It means those has to be positive, otherwise it won't alternate, and then plus minus plus minus plus minus. Okay, so that's an alternating series. Now, to check whether an alternating series converge, there is a very easy test. If I have an alternating series, there is a very easy test which tells us if the series converge. So there are two conditions, basically. If they are satisfied, we can immediately determine that the series converge. So alternating series test. I will state it, tell you how it works, and then I'll show you how it works. So alternating series test. Okay, this test tells me the following. Suppose we have an alternating series. So that sigma -1 to the k plus 1 be an alternating series. Okay, that is the sum equal to a1 minus a2 plus a3. I keep writing to give you a feeling that it's an addition of term is. Okay. Then, if the following are satisfied, so if the series satisfied, the following hold. Two conditions. First, the limit of the AK equal to 0. And if the sequence, so if the following hold, limit of AK equal to 0, and the sequence of terms, the sequence AK, the sequence of term is decreasing, it means A1 bigger than A2, bigger than A3, bigger than A4, etc. Then we can immediately say then the series converges. So I read it again. Suppose you have a series that alternate. If two conditions hold, if those terms go to 0, become very small, and they are decreasing, it means A1 larger than A2, A2 larger than A3, so the terms decrease as we move on. If both conditions are satisfied, immediately we can say that the series converge. So that's what the alternating series test tells us. Okay, under those two conditions, the series converge. So let us see how it works. It works in a very easy way. And then let us see why those two conditions will guarantee that the terms will add up to something. So how it works. Are you guys done writing? Tell me yes or no on chat. Yes. So let's see examples. Example number 1. So the question is, decide if the series converge or diverge. That's really our question. So does the series converge or diverge? So do the series below converge or diverge? And of course, justify. You have to justify. Crucial. Okay, we have every time we have to justify our work. So the first series is sigma the one I started with, to the power k plus 1 over k equal 1 to infinity. Okay, so this is 1 minus a half. So that's absolutely alternating. That's the one I started with. And so on and so forth. Okay. Now here, what's playing the role of AK? I usually don't like to call them AK. I like to call them BK to distinguish them from sigma AK in general. But the book is using AK, so I try to use what the book is doing. So what the AK are not the term. In the alternating series test, the book for the AK doesn't mean the term. What the book means is actually intuitively is that the absolute value of the term. That's really what the AK are. So which is the 1 over k. All right, so I know it's confusing because usually we write sigma AK, and AK has to be in the representative of a general term. For the alternating series, the book is using AK not for the term, for actually the absolute value. So they are using it for those. This is A1, A2, A3, A4. Okay, some other book don't call it AK, they call it BK to distinguish them from those, but not this book. All right, so these are the AK. Now does the series converge? The AK, Chris, are those. This is A1. Why did you put 1 over k? Because what's the absolute value of that term? Minus 1 to the k plus 1. This is either plus 1 over k or minus 1 over k. So in absolute value, this is 1 over k. So this is A1. This is A2. This is A3, A4, A5. So that's the setting in an alternating series test. Now, are both conditions satisfied? Let's see. For the series to converge, the alternating series have tell me that if the term go to 0, and if they are decreasing, I'm done. The series converge. Now, are those satisfied? So let me try. When k goes to infinity, the AK, which is the limit of 1 over k, this is definitely equal to 0. All right, so this is satisfied. Now, are the terms decreasing? What are the terms? Means I'm looking at this sequence. A half, a third. These are the terms, etc. And the question is, are those terms decreasing? It means as k gets larger, are they decreasing? So, what do you think?
Yeah, they're decreasing.
Are those decreasing? It means this number is larger, larger, larger. So absolutely. And now mathematically right, decreasing because in general, what do we have? So AK is 1 over k. AK plus 1, the term that comes after it is 1 over k plus 1. And the question is, obviously, the question is AK larger than AK plus 1? That's what it means decreasing. It means it's the term AK larger than AK plus 1, and the answer is yes. Because k plus 1 is actually larger than k. It means when I flip them, 1 over k plus 1 is going to be less than 1 over k. It means the terms are definitely decreasing. Okay, all right, so AK is decreasing because, sorry. That's my question. The question is AK bigger than AK plus 1? And the answer is yes, because k plus 1 bigger than k means 1 over k plus 1 is bigger than 1 over k. When the denominator gets larger, of course, the fraction becomes smaller. So since AK goes to 0 and the sequence AK is decreasing by the alternating series test, alternating series test, that's the way we will be abbreviating it, the series itself will converge. It means when we add those terms, they're going to add to basically a fixed number. Actually, one of the things we will see, hopefully, not hopefully, we will, is that those terms, as we add them, they will get close to ln of 2. So one of the things we will see about this sum, it means if we start adding those terms, we actually get close to ln of 2, which is like almost 0.69 or something like that. So this is a series where we will be able actually to find its sum. It means the partial sums here will eventually get close to ln of 2. So this is kind of interesting about the series. So let's take up another example. Let me take sigma. Minus 1 to the n plus 1 if you want, or k plus 1 times k over k plus 1. 1 to infinity, okay? And first, let's see what the AK are in this problem. So what's the AK in this problem? In an alternating series, the AK represent what? In an alternating series setting. So this is what I have here, 3/4 minus 4/5 plus 5/6, and so on. All right, so what's the AK in this scenario? Again, I'm expecting chat because that's the only way I can, it seems, work with you today. Right, it's the K over the K plus 1. It's the absolute value of those. That's really why AK. Okay, all right, so now does the series converge or diverge? Let me check what happened to the AK. Is what's happening here when K is large. What's the limit of those as K goes to infinity? When K goes to infinity, this one goes to infinity and this one goes to infinity. But intuitively, the limit is going to be what? When K is large, almost K over K is equal to 1. So, or if we divide both by K, you're going to get this, which is equal to 1. So what can we say about the series now? Is it going to converge or diverge? What can you say? So those terms, absolutely, that's a divergent series. So this one, the series diverge. So this is not 0. The limit not 0. I'm done. The series diverges by the divergence test. Okay, all right, so we have to be, always we have to watch for those. My last example before we go to why really those series, why this test work, and of course it's going to be a very intuitive reasoning. Suppose now my last one is minus 1 to the K plus 1, K over K squared plus 1, from 1 to infinity. Okay, this is again definitely a alternating series, because those terms are always positive, and this will make the sign alternate. Those are positive, and this would make the sign alternate. So in my scenario here, the AK are the absolute value, K over the K squared plus 1. Okay, all right, let's check that out. Now, are both conditions satisfied? This is equal to the limit of K over K squared plus 1. So when K is large, the numerator is almost K, the denominator is K squared, because 1 is kind of negligible in front of K squared when you plug in large values of K. So this is almost like 1 over K, which is going to be 0 intuitively. But let us find the limit algebraically. We divide by k, give me a 1 in here. Divide by k, it gives me a k and 1 over k. So and as k goes to infinity, this goes to 0, but the whole thing, k goes to infinity, will go to infinity, which is equal to 0. 2 is the sequence decreasing? It means the sequence k over k squared plus 1, is it decreased? So question number 2 is the sequence k over k squared plus 1, this one decreasing. Okay, and the question is, this is not easy like the first example I gave you, which was the 1 over k, which is just you look at it and it's very clear decreasing. This is a little bit harder because I have k and k squared plus 1. So when k increases, in this scenario, when k increases, the numerator increase and the denominator increase. So is it decreasing? What can we do about it? So even if I look at the term, like it's 1 over, if k equal to 1, I will have 2, and then I will have 2 over 5. So I don't know, that is 3 over 9 plus 1, 10. So the pattern is not really kind of very clear. Is it decreasing? Zach, tell me it's decreasing, and let's see why, or how can we justify it? Right, when it's not as trivial as the first scenario, one way you can show it's decreasing is by the following. You take the following function, f of x equal x over x squared plus 1. So you go back to calculus 1, f x equal x over x squared plus 1. And then I'm going to make it easy for us, and you guys graph this function. Means you can actually, if you want, so there are 2 ways you can do it. You can graph this function and see what you get. So noted that the function I took at k, it takes the value k over k squared plus 1. And we can basically graph this function. Now, if this function is decreasing, so this is the function, f of x equal x over x squared plus 1. Okay, this function is, of course, it's a decreasing function if we graph it. So it means that if I plug in f of x is decreasing function, okay, hence, in this particular scenario, since it's a decreasing function, then the ak, which is nothing more than the value of the function as k, form hence the sequence ak is a decreasing sequence. Okay, so one way you can decide whether it's decreasing, you take the function associated with it, you can sketch it. If the function decreasing, then the sequence itself is decreasing. So now by the alternating series test, we can apply it at this stage. So by the alternating series test, since the ak goes to 0, the ak form a decreasing sequence, it means by the alternating series test, the series diverges, converges. Okay. As I said, we don't know what it converges to, but we know that it converges. So if we pick up whatever I showed you a minute ago, the algebra system, and start adding and adding the numbers, then we realize that at some point the numbers are not bulging, are not really changing much anymore. And that's really the value of the sum. So now the question, why the alternating series test work? Okay, so what I'm going to do is I'm going to show you very intuitively, very geometrically, why the series actually, this test work. All right, this is the picture. I will show it to you by a picture. So why the alternating series test work? So we have this sum. That's what it is. It's A1. You're taking away A2. You're adding A3. You're taking away A4. You're adding A5, and so on and so forth. That's really what we are doing. That's the type of sum. And to study whether a series converge or diverge is studying the partial sums. That's really what we have. So S1 is A1. S2 is A1. You're taking away a little bit. You're taking A2. And now remember here that the AK goes to 0 and the AK are decreasing. Both conditions, we're going to be using them. The S3, what you are doing, you're taking A1 minus A2, and then you're adding the A3 to it. That's what A3. And so on and so forth. So why those sums will eventually don't blow up? Why are they actually going to get close to something? Right? And this is the intuition behind the idea. So on the number line here, I'm going to put those sums. On the number line, I'm not going to put them, I'm going to put them on the number line. S1 is A1. Actually, I want my number line to be a little bit lower. I want it down here. Okay, that's my line. Okay, S1 is A1. So I'm going to put S1 here on my line. Okay, now what is S2? It's A1, but I'm going to take away something from it. So this is A1, whatever A1 is, but I'm going to take A2. So this is S1. I'm going to go back. Suppose this is A2. So this is going to be S2. That's what S2 is. It's A1. I took A2 away from it. So suppose S2 is 3. If I take 1 away from it, I'm going to go backward. So this is my S2. Now what is S3? S3 is A1 minus A2. It means this is S2. I will add A3 to it. So what is A3? If this is S2, I'm going to add A3 to it. So this is A3. I'm going to add it to it. So my S3 is right there. What is S4? S4 is what? Whatever S3 is, so it's A1 minus A2 plus A3. You're taking away A4 from it. So what is S4? S4 is A3, but you're subtracting something. So you're going to subtract A4 from it. So this is S4. And watch carefully. A3 is less than A2. So when I'm taking A4 is less than A3. So if this is A3, I'm taking A4. A3 is from here to here. I'm taking less from it. So those things are actually getting smaller and smaller. Now what is S5? What is S5? S5 is going to be here. I'm going to move forward by S5, but I move less than before because A4, that's S5, because it's decreasing. A5 is less than A4. So eventually what's going to be the picture and why things are going to start bunching, why those sums are going to start bunching together. Let's see what's the picture here. Let us say this is S, so these are odd. So this is S99. Okay, let me call it S99. So dot, dot, dot. What is S100 is going to be? Let us see what's the difference. S100 is S99. And in my scenario, I'm going to take away A100. So that's in my scenario because it's alternating. So S100 is going to be, they start here, you move by A100. And you remember those A's are becoming small and less. So S100 is going to be right there. And then what's going to really happen? What's going to be S101? It's going to be here. S102 is going to be here. So those AN are becoming very, 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 very small because they're going to 0. So what's going to happen to the partial sum? So every time we're going to have like S1000 here, S1001 next to it. And the distance between those partial sums are becoming really, really, really very small, causing them to bunch up somewhere to a sum S in between. So there is no way for them to diverge. So when the alternating, because we're adding, subtracting terms, those terms are decreasing. So S1, S2, S3, S4, S5, S6, S989, S100. So those sums are really bunching up. S1000, S1001, they are bunching up because those AM become close to 0. My sums are actually becoming close to S. So that's why they don't actually, they start getting close and close together. And that's what's the idea of convergence. It means those sums SK get close to something specific. And that's what will happen when it's alternating. This scenario cannot be used if the terms weren't alternating by any stretch of the imagination. They have to be because we're adding and subtracting, adding, subtracting, adding, subtracting. Okay. So it's an easy test to use and it's going to be useful for us. And I want you to notice one thing and then we let go. Watch very carefully the difference here. This series, this alternating series converges because we add, we take away, then we add. And the terms we're adding are getting smaller, smaller, and heading towards 0. So this one, etc., converge. However, when we drop the minus sign, what will happen? What happened when we drop the minus sign? Will it converge or diverge? Diverge. Okay, because that's the integral test. So this means that for a series to converge, two things should happen. Either the term has to become small, like 1 over n squared. They have to be really become very small, which doesn't happen in this scenario by integral test. And other things that can cause the convergence, if this compensation here. So we're taking away, but then we're adding. So we're not keep adding for it to blow up. We're taking away, yeah, but then we're adding a little bit. And then we add, but then we take away. And then we add. So this compensation gives us the hope that we're actually going to get close to something. Right? So I stop right here today. The homework is fairly simple. But as you guys expect, MATLAB, unfortunately, is not asking you to show your work for those problems. But we will, in my quizzes, I will ask you to show the work. So be very careful with that. So as long as you're doing those homework, make yourself, you know how to show AK goes to 0, and you know how to show the series, the terms decreases. MATLAB is not asking you to do that, but I cannot change MATLAB. All right. So you will be able to do all the problems except the last one that I will talk about it tomorrow. So class is dismissed. And if any student have some time, they can stay with me for a minute or so to see what's really going on, why you guys are muted. Okay, otherwise the class is dismissed.